All right, so where I wanted to start off this evening is in chapter 14. Last class we did some practice problems that relate to chapter 14, but right now I want to talk about some names. And I told you last lecture that you have to know the common names. So you've got to know the common names of the first five carboxylic acids. So common names. So you have to have formic acid, acetic acid, propionic, butyric, and valeric acid memorized. Beyond those, you see here you have caproic acid, caprylic acid, capric acid, palmitic acid, and stearic acid. You do not have to have those ones memorized, okay? But the first five, you do have to have their common names memorized. So we went over that in detail during the last class. Well, what about benzoic acid derivatives, okay? By now, you know that when you have a six-membered ring that has double bonds that alternate like this, we call that benzene. So this is benzene. And another way to draw benzene is just to draw a hexagon and then put a circle in it like that. So this is, the benzene portion of benzoic acid. And then we have our carboxylic acid attached to it, and that's where the name benzoic acid comes from. It's a carboxylic acid derivative of benzene. Well, we can have further derivatives of benzoic acid, right? You're probably aware of toluene, right? I went over that with you in class, that if you have a benzene ring and if you put a methyl group on it, then it becomes toluene. Toluene. So it's not that much of a stretch to see that if you take benzoic acid and you add a methyl group to it, you get what's called toluic acid. Now, you don't have to have that name memorized, not at all, but I just want you to understand where it comes from. Here we have what's called ortho-bromobenzoic acid. We have a bromine on there. Here we have meta-iodobenzoic acid, and this one here is called phthalic acid. You don't have to have that one memorized either. All right, so but these are all just derivatives of benzoic acid. Why? Because they all have benzoic acid as a part of their overall structure, right? They've all got benzoic acid in there somewhere. This one's got like two benzoic acids, right? Here and here. Anyhow, so that's why these are considered benzoic acid derivatives. All right, let's move on. What about carboxylic acids with a phenyl substituent? Now, don't mix up phenyl with phenol. Now, I told you earlier what phenol was. So phenol is when you have a benzene ring, okay, and it's got a hydroxyl on it. So that is phenol. That's just the name of this molecule. It's called phenol. A phenyl, okay, when you have YL, not phenol, phenyl is a group. You know how we've learned methyl group, right? We've learned ethyl group, we've learned propyl, so on and so forth, right? Well, a phenyl is just a type of hydrocarbon group, like a methyl, ethyl, propyl, phenyl. Okay, so when a benzene ring is considered like a substituent, instead of calling it benzene or benz or something like that, we call it a phenyl. So when would you use a phenyl? Okay, here are some good examples of when you would use a phenyl. Now, by now, you know that if you have CH3 with a carboxyl group attached to it, right? You know that this is called ethanoic acid. That's the IUPAC name. And you know that the common name is acetic acid. Acetic acid. Well, what would happen if we replaced one of these hydrogens with a phenyl, right? Just like adding a benzene to it. Well, we treat that phenyl as a substituent. So since this is our first carbon and this is our second carbon, maybe I should be proper here with my colors. So you have your first and your second carbon, you have the phenyl on carbon 2. This would be 2-phenyl ethanoic acid. Conversely, if you were to use the common nomenclature, this is called your alpha carbon here. And so you have alpha phenyl acetic acid. All right, so again, a phenyl is just a benzene ring that is, instead of being a benzene or a parent, it is just a substituent. Here's another example here. We don't have a lot of room, but you know by now that if you have 3 carbons, right, 1, 2, 3, and then a carboxyl group, that the IUPAC name for this is propanoic acid, whereas the common name is propionic acid. So if we number the carbons using IUPAC rules, 1, 2, 3, on the third carbon, we have a phenyl. Right? I told you that a phenyl is when you have a benzene ring as a substituent. So when it's just hanging off of something, this is a phenyl. No, a phenyl group. There we go. Now, again, just more review. If you want to name it using the common nomenclature, this is the alpha carbon here, this is the beta carbon. So your phenyl is on the beta carbon, and this would be beta phenyl propionic acid. All right, there we go. So a little practice on using a phenyl, so a benzene ring, as a substituent, not a parent. All right, there we go. Well, everybody who studies organic chemistry has to learn a few dicarboxylic acids. And these are the only ones that you have to learn in this class. Now, in order to have a dicarboxylic acid, you have to have a minimum of 2 carbons, right? In order for you to have 2 carboxyl groups, right, here and here, you have to have a minimum of 2 carbons that you see here. Now, the IUPAC names go from when we have 2 carbons to 3 carbons to 4 carbons to 5 carbons to 6 carbons. They go ethane dioic acid, propane dioic acid, butane dioic acid, pentane dioic acid, and hexane dioic acid. You have to know the IUPAC names, but generally speaking, students don't struggle with the IUPAC names a whole lot. But if you look at the common names, I mean, these just come way out of left field. I mean, these are all just historical names, okay? And so the way that my students helped me learn this a long time ago is with the acronym OMGA. Okay, I know what the acronym is. I'm trying to draw it out the right way here. So this is something my students invented. It doesn't mean anything to me, but I've never forgotten it. The students come up with all kinds of funny things to memorize stuff. So they said, "Oh my stars, go away." Okay, again, it's just something that my students told me, and I never forgot it. So you have the letters OMSGA, and they stand for oxalic, malonic, succinic, glutaric, and adipic acid. And so it would be wise, which is another way of me saying you've got to memorize oxalic acid, malonic acid, succinic acid, glutaric acid, and adipic acid. And you can remember that the simplest possible dicarboxylic acid has to have at least 2 carbons, right? Number of carbons. So 2, 3, 4, 5, and 6, okay? So oxalic, malonic, succinic, glutaric, and adipic acid. And I would wager that if somebody here has taken biology class, you might have seen some of these dicarboxylic acids before, maybe 1 or 2 of them. Anyhow, there we go. A slide like this where I tell you, hey, you guys, you got to memorize something. I mean, I could sit here and talk about it all night and try to help you memorize it, but the best way is for you to sit down and just kind of do it on your own and try to maybe you could make flashcards or just write it out a few times. That often helps students, but you have to know the first 5 dicarboxylic acids: oxalic, malonic, succinic, glutaric, and adipic acid. Okay, well, where do we find carboxylic acid? The answer is everywhere. Okay, soap, for example, just regular bar soap like Ivory soap or Irish Spring or any kind of soap like that. It's just a derivative of a carboxylic acid, and I'll explain that later. But you find carboxylic acids in food, for example, citric acid, right? I'm sure that a lot of you know that citric acid is found in lemons, limes, and oranges. Many of you have probably heard of lactic acid, right? Maybe not from the fermentation of sugars, but probably if you've ever done a strenuous workout, and you wake up the next day and you feel sore, that's due to a buildup of lactic acid in your muscles due to fermentation. And we'll talk about that later on in the class in another chapter. Tartaric acid is found in baking powder, tartaric acid. If you like the sour taste of Granny Smith apples, that's malic acid that produces that taste. And then it says here that fatty acids are long-chain carboxylic acids that are found in plants and animals. So, you know what? When I was a student, I always wondered, what is a fatty acid exactly? Okay, what the heck do they mean by a fatty acid? Well, everybody knows, or I'm sure you all know by now, what a carboxylic acid is, right? This is just a generic carboxylic acid. So if you have your carboxyl group, like that, and you have 2 carbons, that's acetic acid, right? That's the main acid that's found in vinegar. It is not a fatty acid. In order for a carboxylic acid to be a fatty acid, all it has to have is a long hydrocarbon tail attached to it, okay? That's all. So the only difference between a fatty acid and things like acetic acid or formic acid is the long tail. Now you might be wondering, well, why would this be called fatty? It's because the carboxyl group is polar. Okay, this part of the molecule is polar, but all this giant tail here is going to be nonpolar. Okay, it only consists of carbon-carbon and carbon-hydrogen bonds. We went over that a lot in the alkanes chapter. And since that is nonpolar, that is what we call like the fatty portion, because fats are nonpolar. Okay, they're not soluble in water. If you've ever tried to wash a greasy pan or something with just water and no soap, doesn't work very well, does it? Right? Because fats don't dissolve in water because they are nonpolar. All right. Here are some structures of some of those acids: citric acid, lactic acid, tartaric acid, and malic acid. You'll notice that tartaric acid and malic acid are dicarboxylic acids, right? They both have 2 carboxyl groups on them. Lactic acid only has 1. Also, you see that they have a bunch of hydroxyls on them, so that's kind of interesting. They must be really soluble in water. And if you look at citric acid, look at this. It's got 1, 2, 3 carboxyl groups on it. So, citric acid, there you go. There's a carboxylic acid that some of you might even consume that every day. Maybe you have an orange every morning at breakfast or something, or you like lemons in your water or something. So there you go. All right. Reactions involving carboxylic acids. And I'm not going to spend a lot of time on this slide, the oxidation of a primary alcohol, because we've talked about this a lot already this semester. And by now, you should remember that when you take a primary alcohol and you oxidize that, first it gets oxidized to an aldehyde, and then it can get oxidized again to a carboxylic acid. Okay, so we've talked about that a lot in this class. Now, what about carboxylates? Okay, now it says here a carboxylate anion formation. Hear ye, hear ye. Listen to me very carefully, people. Whenever you hear carboxylate, another way to describe carboxylate is to call it a carboxylic acid salt. Okay. The thing is when you have a carboxylate, it means an anion, right? It just means something with a negative charge. So when you have a carboxylic acid salt, that's when you actually have like a cation with it. So if you had sodium here, then this would be a carboxylic acid salt. Anyhow, so let's get back to it here and talk about forming a carboxylate anion. So it says here that carboxylic acids behave as acids. Well, that shouldn't be much of a stretch. They are acids. It's in their name. Because when they dissolve in water, they will deprotonate to form a carboxylate ion and a hydronium ion. What's the definition of an acid that you would have learned in Chemistry 101? An acid is an H+ donor, something that donates a proton. Well, here's my carboxylic acid right here. What's the proton that's going to be donated? It's going to be this proton here that gets donated. Who does it get donated to? Well, this is showing the dissociation of the carboxylic acid in water. So it's going to donate that proton to the water molecule. Now, if H2O takes on H+, what do you end up with? You end up with H3O+, which is called hydronium, and you're left over with the carboxylate anion. Remember, 8 in organic chemistry: carbonate, nitrate, sulfate, chlorate, right? These are things that have negative charges. So here's my negative charge right there. Now you might be wondering, well, how much do carboxylic acids dissociate, Mr. Dion? Well, since they're weak acids, where was I? They don't dissociate all that much. They actually dissociate less than 5%. Okay, so they're not strong. Right, a strong acid would be something like sulfuric acid or hydrochloric acid. Those dissociate 100%, but weak acids dissociate much less. All right, neutralization reactions. If you go back to your general chemistry days and you think about a reaction like this. When you take hydrochloric acid and you treat it with sodium hydroxide, okay? Hydrochloric acid is an acid. Sodium hydroxide is a base. What happens when you mix an acid and a base? First of all, I wouldn't do this. It's dangerous. But if you do, you end up with sodium chloride, which is a salt, right, plus water. Now, the thing is that HCl is a strong acid. What's going to happen when we take our carboxylic acid and we treat it with a strong base? Because a carboxylic acid is not a strong acid. It's a weak acid. Well, we still get a neutralization process. The base acts as a proton acceptor, so it takes a proton from the carboxylic acid, okay? And we're left over with water and the carboxylate ion. However, since the carboxylate ion is in the presence of a sodium cation, we get a carboxylic acid salt. So watch carefully. Here's my carboxylic acid. It's going to donate its proton, right? I told you in the last slide that an acid is a proton donor. Who's going to accept that proton? The hydroxide, which is the base. They're going to join together to form water. What are you going to be left over with? You're left over with the carboxylate and the sodium cation. So we call that a carboxylate salt or a carboxylic acid salt. Notice that we use the word salt, right? It's not table salt like sodium chloride. However, it is a salt because a salt is nothing more than a metal, and a non-metal. Now, sodium is a metal, and everything that's in the carboxylate is a non-metal. Carbon is a non-metal, oxygen is a non-metal, hydrogen's in the R group, those are non-metals. Okay, so that's why it's called a carboxylic acid salt. You got to know your acid-base chemistry in organic chemistry. So this kind of things are very important. With that in mind, let's take a look at a couple reactions. What would happen if we took these carboxylic acids, very common carboxylic acids, and put them in a strong base, like sodium hydroxide? Let's take a look. If we took acetic acid or ethanoic acid, I use acetic acid because it is the common name. It's more common than saying ethanoic acid. If you take that and you put it in sodium hydroxide, literally the hydroxide is going to take this hydrogen like that. It's going to take it. So what are you going to be left over with? You've taken the proton and you combined it with the hydroxide. You're left over with water. Well, what's left over from that then? You've got this portion, which is going to be here, the carboxylate, and you've got sodium cation. So you end up with the carboxylate salt, or the carboxylic acid salt, means the same thing, and water. You can see the exact same thing happening here with the benzoic acid, right? The hydroxide is going to take that proton. You're left over with the carboxylate salt and water. The same old thing is happening in both of these reactions. You're taking an acid plus a base. You're getting a salt and water in each case. Water. There you go. You probably noticed these sassy names that are here, things like sodium ethanoate, sodium benzoate, sodium acetate. And you might be wondering, do I have to name those? And where do they come from? The answer is yes, and let me show you. How do you name a carboxylic acid salt? The first part's the easiest. All you're going to do is list the cation's name. So let's say we had this. Our cation is sodium. So you would just write down sodium. Now, what's the rest of it going to be? If you look at this part here, the carboxylate, where did that come from? That came from this carboxylic acid. All I have to do is draw it out with the hydrogen, and this would be benzoic acid, right? It's one of the acids I asked you to memorize. So what you do is you drop the oic acid. This part here, oic acid, gets dropped, and you change the suffix to O8. So here it says 8, but it should, or no, so sorry, if it's, actually I have not a mistake here, it's not a major, anyhow. So you see it says oic acid, it should say ic acid, and then you replace it with 8, right? So if you put, there we go, and it would be benzoate, okay? So sodium benzoate. And so that's what we'd call this. It would simply be sodium benzoate. All right, there you go, sodium benzoate. Where would you find salts with carboxylic acid? Well, you probably remember that I told you earlier that hand soaps, like bar soaps, like Ivory or Irish Spring or whatever, Dove, I don't know, those are all carboxylic acid salts, okay? Those soaps just come from animal fat that's been converted into a carboxylate salt. They're also used in preservatives and antifungal medicines. They have lots of different uses, carboxylic acid salts. In fact, if you start looking at the ingredients on all kinds of different packaging or different, different compounds that might be on cleaning things or, soaps even or toothpaste in your house, you might end up seeing things with suffixes like benzoate. Well, let's talk about esterification. As I told you during our last lecture, esterification might be the most important reaction. It isn't. I mean, they're all important. But esterification is an extremely, extremely important reaction for you to know in Chemistry 102. The reason why I say that is because before the pandemic, we always used to give our students the ACS final, okay, the ACS final exam. And ACS is just the American Chemical Society. We don't do it now, and we're not going to do it until the pandemic's over for, it's actually legal reasons. It's a long story. But anyhow, the ACS final exam was basically a standardized exam provided for any Chemistry 102 students in any college or university anywhere in the country. So we'd have thousands and thousands and thousands of students all writing the same exam. And the reason it was great is it gives us an idea about where do our students stand with respect to Chemistry 102 students in the rest of the country. And in that exam, they would always have several questions about esterification. So it's something that's very important that you understand, okay? Esterification is nothing more than it's the formation of an ester from a carboxylic acid, I'll just draw the shorthand here, from a carboxylic acid and an alcohol, okay? So here it is summarized right here. A carboxylic acid reacts with an alcohol, and what do you get? You get an ester and you get water. Look at this right here. You take a carboxylic acid, you treat it with an alcohol, you get an ester and water. Now, something is missing here, in my opinion. And for the acid, I like to just write H+. A proton represents acid, and it's probably also wise to heat this up. Why is it wise to heat it up? Because if you're trying to drive water out of a reaction mixture, water has a boiling point of 100 degrees Celsius. So if you're able to boil it, then it can just escape as a gas, and then it's not going to come back in your reaction. Okay, no break. And let's move on to esters. Okay, and we're going to talk more about esterification, of course, and we'll look at an ester. The reason esters are in chapter 14 is because an ester is just a derivative of a carboxylic acid, right? If you draw the generic structure of a carboxylic acid, here's a carboxylic acid. An ester is just where you replace the hydrogen with another R group, right? This is an ester. So they are derivatives of carboxylic acids. And as you saw back here, you can make them from a carboxylic acid. So what about them? It says here they're mildly polar, somewhat water soluble. I'd say that depends on the ester. The smaller the ester, probably the more water soluble it'll be. Here's something that you'll find really interesting, though, is that they're found in many foods, in natural foods, things like strawberries, raspberries, bananas. For example, if you like the odor of bananas, and a lot of people do, isoamyl acetate, which is the common name of banana oil, its IUPAC name is 3-methylbutyl ethanoate, and we'll get into the nomenclature. But again, the ester is what gives the fruity, good, banana smell. Things like juicy fruit gum, right? That's an ester that provides that fruity smell. The smell of a pineapple, if you've ever wondered what that comes from, it's from a compound called ethyl butanoate. These can be made in the lab very easily, so it's always fun to do labs where you get to make a few esters. And then isobutylformate, that's the common name for isobutylmethanoate. That's the odor of raspberries. And if you could just do if you just did a quick Google search, just type in esters, and odors, and you'll come up with all kinds of them, cherries and oranges, and you'll see that, yeah, and all these delicious odors come from esters, okay? So finally, something in organic chemistry that's not stinky or foul smelling or something. Esters smell really nice. Anyhow, what about the boiling point of an ester? Right, we've talked a lot about boiling points in this class, that a carboxylic acid has a higher boiling point than an alcohol. Then an alcohol has a higher boiling point than an aldehyde or a ketone. That has a higher boiling point than an alkane, and we talked about hydrogen bonding and dipole forces and London forces. Well, where the heck does an ester land on the spectrum? Because it says here that esters are mildly polar. Well, it says here that they boil at approximately the same temperature as carbonyls with a comparable molecular weight. Now, what is a carbonyl? I went over this, I believe, in the last lecture, but in case my memory doesn't serve me correctly, carbonyls is just a fancy thing that organic chemists love to use, and what it means is aldehydes, and ketones. Yes, I'm aware that other functional groups have carbonyls in them, right? A carboxylic acid has a carbonyl, right? An ester has a carbonyl. An amide has a carbonyl. An anhydride has a carbonyl. But basically, the crux of the matter is this, is that esters have similar boiling points to aldehydes and ketones that have molar masses that are close to them. All right? Well, let's get into the nomenclature of esters. You got to know how to name an ester. We saw some really interesting names on the last slide. And here's how you do it. It says, esters are formed from a reaction with a carboxylic acid and an alcohol, which is reflected in the naming. So here's a generic structure of an ester down here. Now you notice that there's two bonds between carbon and oxygen. There's a double bond between carbon and oxygen, and there's a single bond between carbon and oxygen. The portion that has the single bond to carbon, we call this the alcohol portion of the ester, right? You see alcohol right here, okay? The other part that's got the double bond to carbon, we call that the carboxylic acid portion, okay? So this portion over here is the carboxylic acid portion. So how do you name the ester? It says you use the alkyl group as the first part of the name, and that part comes from the alcohol part. So whatever this R group is here, you see this R group right here that's on the alcohol portion? That is the alkyl group. Alkyl group. So what that mean is that if this is OCH3, it would be methyl. If it was OCH2CH3, it would be ethyl, propyl, whatever that alkyl group is, okay? Then the base name, or the parent, comes from the carboxylic acid part of the structure, okay? You determine what the carboxylic acid would be if instead of OR, if this was OH, right, like a carboxylic acid. So you name the carboxylic acid, you drop the ic acid or the oic acid, and you change it to OH. All right, so let's take a look at an example here. We have an ester right here, beautiful ester. You notice that there's a carbon-oxygen double bond. There's a carbon-oxygen single bond. So the part with the single bond, that's going to be our alkyl group. You can see that it is an ethyl. That means the name must be ethyl something. Then if we look at the carboxylic acid portion, that's all of this portion here. If that was a carboxylic acid, it would be CH3, CH2, CH2, carboxyl. That would be butanoic acid. What do? We drop oic acid and we replace it with O8. So we get ethyl butanoate, like that, ethyl butanoate. Let's take a look at this example right here. You can see the alkyl group is bigger. Here's our alkyl group, and it is a propyl group, so this must be propyl something. Then if you look at the part that comes from the carboxylic acid, this part right here, it's a 2-carbon carboxylic acid. We're just going off of IUPAC names. This would be ethanoic acid. you drop the oic acid and you change it to O8 and you get propyl ethanoate, like that. All right, let's try an example here together. And I'm going to use a bond line structure or two here, and I want you to try to come up with some answers for me. I'll give you a few minutes to try to solve these three, and I'm going to go get a drink of water. Does anybody have a name for any of them at all? Okay, hey, I like the way you think, Sadie. Methyl propanoate, absolutely. So tell you what we'll do here, and we're going to do even more work here. We're going to do IUPAC names, and we're going to try and do common names too, because you can do both for an ester. Let me show you what I mean. So what Sadie said for the first one is she said, okay, come on, I've got a methyl group right here. So I can start with methyl, right? If I have a 3-carbon carboxylic acid, it would be propanoic acid. So this would be methyl propanoate. Absolutely perfect. Now, if we wanted to give it the common name, the only thing that's going to change in the common name is the part that's derived from the carboxylic acid, right? Because if you have a 3-carbon carboxylic acid and you give it the common name, it's propionic acid. So what you do with common names is you drop ic acid and you change it to 8. So let me show you. So here we have methyl propionate. Methylpropionate would be the common name. And if you're thinking, oh, come on, this is too much. I got to learn 2 ways to name all these things. Yeah, it's just the way it is in organic chemistry. Common names are common for a reason. Chemists love them, so they just stick around. So if you are working in the hospital and you see something that has propionate or propanoate, you have to know that they're the same. They mean the same thing. Okay. Does anybody have an idea for the next one? Even if you only got part of it, I'm happy to take any suggestions. Okay. Yeah. No, you're not off at all. No, Sadie, you're not off. Don't remember. This is a place. This is a safe space. Okay, you can say any name you want. Okay. Let's Okay, Sadie, if you want to name the next one, let's go for it. So first we'll do the IUPAC name, and you get the right the right place to start. Right, we have an ethyl group here, so this must be an ethyl. Now the carboxylic acid, maybe you guys you haven't seen these ones enough. So the way you would name this carboxylic acid, it would be cyclopentyl cyclopentane carboxylic acid. Carbox acid. Okay, so we're going to drop the ic acid and we replace it with 8. So this would be ethyl cyclopentane carboxylate. Ethyl cyclopentane carboxylate. Son of a gun. I need a new prescription so bad. Carboxylate. There we go. All right. And I see where you're going there with the cyclovalerate, right? We don't really do the common names for the cyclic ones. So I just mentioned that during the last lecture. Let's give this one here a try. Does anybody have any ideas about this one? Or where I could start with this one? Guy in the middle guy. Anything? No? Okay. Well, what about this? Could I ask you guys what you think this alkyl group would be here? You recognize that alkyl group? One you had to memorize? It's a common name. Okay. If not, yeah, thanks, Gavin. It's isopropyl. Son of a gun. Perfect. So it's isopropyl. And then if we have 2 carbons, it would be isopropyl ethanoate. Would be the IUPAC name, and the common name would be isopropyl acetate. Isopropyl acetate, right? Because it's only got 2 carbons. Acetic acid becomes acetate. There you go. So a little practice there. Do you find that feeling a little more confident? Even if you're like, I just need some more practice, Mr. Dion, but I have the idea. Anybody feeling like you kind of have the idea? Okay. All right, good. Thanks, Gavin. Perfect. Let's move on from there. Let's talk about naming esters again. And if you want a little, kind of help, this is something, that is comes right out of our textbook. It was put together by Dr. Deniston herself. And, she basically said, if you can name a carboxylic acid salt, you can name an ester. Kind of like the same thing, right? You know how when we learned tonight, we said, okay, well, let's look at a carboxylic acid salt. First, we started with the cation, sodium. Same thing with an ester. First, you look at the alkyl group. You put that first, right? And then the rest is the same, right? This would be ethanoate. This would be ethanoate. Doesn't change, okay? So again, if you understand how to name a carboxylic acid salt, naming an ester isn't that much of a stretch. All right. You guys want to try one more? Try one more. One more, and then we'll give it the old go for it. We'll do something different here. There, see if you can name this ester, and then I promise I'll leave you alone with nomenclature. I won't bother you for a few seconds. Give it a try. And just come up, well, you can come up with a common name and a IUPAC name. And if somebody has one, just scribble it down in the chat. All right, who's got an idea? Anything? Butyl propanoate. Looks reasonable to me, right? I've got a butyl group right here. So I must start with that, butyl. And how many carbons do I have here? I've got 1, 2, 3, 4, 5. So it must be butyl pentane. So if I had pentanoic acid, it becomes pentanoate. So butyl pentanoate, right? Because we got 5 carbons in the carboxylic acid portion. If I wanted to give this the common name, it would be butyl. Instead of valeric acid, it would be valerate. Like that. Yeah, no problem. I miscount carbons all the time. Part of life. Anyhow, again, if you need more practice, what would you do? You would go into the practice problems that I have suggested. I've also posted the answers to those. They can be found under the content tab. So you have all the answers there. Give them a try. Do all of them. Okay. No, it's not. I'm not saying do as many as you can. I'm saying do all of them. Okay. Every last one. All right. Well, let's get into the nuts and bolts here of reactions with ester. So here's the esterification reaction. That's what's being shown here. This is esterification, which is nothing more than the formation of an ester from a carboxylic acid and an alcohol. You can buy, tons of different carboxylic acids. There's lots of alcohols available on the market. So all you have to do is take them and heat them in the presence of acid. Okay, heat is also required. And you form an ester and you form some water. So all you have to do is separate the ester from the water. And there are ways to do that. It's not covered in our class, but there's some interesting ways to do that. And there you go, my friend. You just made an ester. Okay, so esterification, extremely, extremely, extremely important reaction that you know that when you take a carboxylic acid plus an alcohol in a strong acid and you heat it up, you produce an ester plus water. And you got to know that it's called an esterification reaction. Well, once you get an ester, what the heck can you do with it? We'll look at that in a second. But before we do that, let's look at a specific example. Propanoic acid or propionic acid. Very common carboxylic acid. Doesn't cost a lot of money. Very cheap. Methanol, that's just fondue fuel. You can get that down at the grocery store, okay? If you heat that up with a strong acid, you can form an ester. Here's the IUPAC name on the top. Excuse me. There's the common name on the bottom, and you also form water in the process. Well, I alluded to this during the last class, okay? Which is, how do we break an ester apart? It's called the hydrolysis of an ester. If you think about what the word hydrolysis is, lysis just means breaking something apart, and hydro denotes that it's done in water. However, when we hydrolyze an ester, we have two possibilities. We can do it in an acidic environment in water, so we can do it in acid, or we can do it in a basic environment in water. So we can hydrolyze an ester in base. Okay? It's very important that you know the difference between hydrolyzing an ester in acid or base. Okay? It says here, you can do the reaction uncatalyzed, but it's very slow. So the best way to do that is to use heat. Now, before we have our break, okay, we will take a break in a little bit, but I have a few more things I want to share with you, okay? I need you to pay close attention here to something. Here is the reaction that shows the acid hydrolysis of an ester. You take an ester and you put it in water, you heat it up with acid, you produce the carboxylic acid and an alcohol. Why? What's going to happen? Watch carefully. You see how there's a carbon-oxygen double bond and there's a carbon-oxygen single bond? Well, a carbon-oxygen single bond is weaker than double bond. Therefore, that's the bond that's going to get broken. Okay, that's the bond that's going to get broken. You've also got H2O. So on the carbon, you're going to attach the OH. And on the alcohol portion, this portion here, you're going to attach the hydrogen right there. Okay? Now, this is the part that, if you're very astute, you're probably noticing something and being like, what is going on, Mr. Dion? It's the exact same reaction that we just saw a few minutes ago for esterification, right? Let's go back and look. We go back here to the esterification reaction. Watch carefully. Carboxylic acid plus alcohol gives you ester and water. Let's go back to the hydrolysis. It's ester plus water gives you carboxylic acid plus alcohol. You're like ready to pull your hair out saying, well, I see that the arrow is reversible, but how do I know when it's going to do what? Well, the answer is this. Let me go back to this one here. Okay? And our book doesn't really go into a ton of detail about this, but let me explain it to you. It's all about the equilibrium process, right? You see that the reaction is in equilibrium. Well, you probably learned Le Chatelier's principle in Chemistry 1, so Chemistry 101, which is that when you have a system at equilibrium, if you disturb the system, in some way, it's always going to react so that it reestablishes the equilibrium. And so the answer is this. Here you go. Here's your answer. In order to actually form the ester, what you've got to do is remove the water. If you take the water out of the reaction mixture, it's going to push the reaction back in this direction towards the ester and water. Why? To reestablish the equilibrium. So that's the answer. You've got to remove the water. Conversely, if you're hydrolyzing the ester, you add a ton of water to it, okay? And that's going to blow it apart, and that's going to force the equilibrium in this direction, okay? Now, I'm never going to ask you to explain that to me or write me an essay about it or something like that, but I like my students to understand why something is the way it is. I don't just want to tell you, hey, memorize these reactions and you don't have to understand why. I want you to have a bit of an idea why the heck it does what it does. So, if we had an ester, let's say we had propylpropanoate, which is propylpropionate, same thing, and we treated that with a lot of water. We're not removing the water. We also treat it with acid and heat. What's it going to do? It's going to break the carbon-oxygen single bond. And you're going to make, from this portion, a carboxylic acid, and from this portion in pink, you're going to make an alcohol. Give me a thumbs up if you're with me, even half of the way, just like, yeah. And if you have a question, hit me. I'm ready. Okay, cool. Not an easy subject, esters. Okay, if it was easy, anybody off the street could do it. Well, before we take our break, I want to show you one more reaction. Okay, one more reaction, and it's the basic hydrolysis of an ester. So it's just taking an ester and hydrolyzing it, so putting it in water. But now instead of being an acid, right before we had acid, now we're going to do it in base. And it's got a super cool name, okay? It's got its own special name. It's called saponification. Going back here, the name of the reaction is acid hydrolysis of an ester. Nothing exciting. When you do the basic hydrolysis of an ester, it's called saponification. It's got its own sassy, little fancy name there. Saponification is just another way of saying making soap. So if you're wondering, is this how soap is made? Yes, this is how soap is made. What we do is we take the ester and water, and we mix it together, but instead of being an acid, we put it in base, and we cook it up. Now, we saw that when we hydrolyzed the ester in acid, we ended up with a carboxylic acid. Well, hear ye, you're not going to have an acid existing in a basic solution, okay? What would happen? Think about it. If you were to hydrolyze it, and you ended up with a carboxylic acid, and if it's in base, we saw that this evening. The base is going to remove the proton to produce the carboxylate, right? That's why we went over that earlier this evening, plus water. So instead of ending up with a carboxylic acid, since you're in base, you end up with a carboxylate. Give me a thumbs up if that makes some sense. You're like, of course, Mr. D. And if I'm in a strong base like sodium hydroxide, I'm not going to have acid kicking around in there. The base is going to neutralize it. We went over that earlier this evening. All right, thanks. Okay, perfect, great. So here's an example how soap is actually made. And if you're interested, and I was going to say I challenge you, but no, I don't challenge you. But if you're interested, if you go on YouTube and you type in saponification of fat, you will literally find almost Avogadro's number of videos of people making soap in their kitchens from animal fat, like literally beef fat, which is stearic acid, or tallow. They'll take beef fat or any chicken fat, and they do all kinds of experiments in their kitchens, and they'll try to make soap. So if you're wondering, what about my hand soap? It's bar soap. Does that come from an animal? Yeah, probably. Okay, normally comes from animal fat. So what they do is they take a fat, which is a triglyceride. Later on, we're going to look at the structure of triglyceride even more, but I'm sure you've all heard of triglycerides, right? If you've ever had a blood test, you look at your triglyceride levels and your LDL and your HDL and those kinds of things. The triglyceride is nothing more than 3 esters. Look, you've got an ester here, an ester here, and an ester here. And they're all on the same kind of backbone, if you will. So that's what a triglyceride is. Now, if you take that animal fat, a triglyceride, and you heat it with a metal hydroxide, like when it says MOH here, just means something like sodium hydroxide or potassium hydroxide, whatever. You end up hydrolyzing all of the carbon-oxygen single bond. Shit, I took the wrong one. Sorry, pardon my language. Anyhow, you break all those bonds here, you end up with all these carboxylate salts, and you end up with this molecule, which is called glycerol, or 1,2,3-propane triol. So here's the answer. This is what soap is. That's what I wash my hands with? Yeah, it's just the carboxylate salt of a fatty acid. Because, and if you're like, well, why is it a fatty acid? Because these tails here, these R groups, are big, okay? Anyhow, so that's how soap is made, and that's the whole process of saponification. I didn't even think about looking up videos about saponification until one of my students told me, like, hey, Mr. Dion, I saw somebody make soap on YouTube, and then I looked and like there's piles of videos of people making soap. Some are good, some aren't so great. So if you've ever wondered how the heck does soap work, well, let me show you, and then we'll take a break. So one of these right here represents this. You have your carboxylate, right? You have your cation, okay, and then you have a big hydrophobic tail, okay, like that, some kind of big hydrophobic tail. So that is what's represented here with the blue sphere. Okay, it's got a blue sphere, and then you've got this red tail coming off of it, okay, that you see right here. So these are all fatty acids, okay? Now, in the middle, this is dirt, okay? This is dirt or grease. And this is how soap works. When you wash your hands, the reason why you can't wash your hands with just pure water, you can't get the oils off of your hands, is because the oils on your hands are hydrophobic, right? They're not going to dissolve in water, which is hydrophilic, which is polar. So when the soap interacts with the dirt, you see all the tails, all the hydrophobic portion, the tails that are just carbon-hydrogen bonds, those interact with the dirt and oil and grease. And the carboxylate portion, so these are all the carboxylates, right? O minus, right? Right. These are all the carboxylate portions. Those interact with what? The water, because this part is polar and this part is non-polar. So they form this little bead here, which is called a micelle. Now, obviously, these are microscopic, but the grease gets trapped inside those micelles and get washed down the drain. Okay, so that's how soap works. It says here, simplified action of soap, but good enough. All right, why don't we stop there for now, and we'll take a little break. Let me just